Welcome to this course on electrical machines 1, where we will discuss about transformers and DC machines. These are the two major topics, and we will begin with transformers. Transformers, as we will see, will generally consist of a magnetic core material made of soft iron, over which there will be at least two coils wound, and one of the coil will be energized with AC source of known frequency, and in the other coil will get voltage of same frequency, but at different levels. So, that is primarily the job of a transformer is, that is, suppose you have a 200 volt 50 hertz supply, you require 400 volt 50 hertz supply, then I will use a transformer to change the level of the voltage from 200 to 400 volt, keeping the frequency constant. It can be similarly a step down situation, where you have a say 400 volt, you want to step it down to 100 volt level, then use a transformer. Transformer is a static device, its efficiency is very large. In case of power transformer, efficiency could be as large as 99%, unlike a rotating machine efficiency, which may be 80%, 85%, very good efficiency, because there is no rotating parts in it. There will be of course losses, which accounts for that 1% or 2% loss in power, that is there, because of conductors will carry current, it will have a I square R loss, and also core we will see when it is having a time varying flux, then also there will be heat loss inside the core of the material. Anyway, those things we will discuss in detail, but it looks like then we have to deal with these situations. That is, suppose you have a magnetic core of this kind, okay, and it has got a thickness like this. In 3 dimension I am trying to draw, okay, and it will be like this. So, this is called, it is a made of soft iron, and I have drawn it right now as a solid iron block. We will see what is to be done, because solid irons are not used, but this is the structure of the iron, and over which there will be coils wound like this. Okay. When there is a single coil and there is a core like this, core material, then if this coil carries current, it will produce flux inside the core. So, we start with magnetic circuit. Okay. We just review that, because that will be essential in understanding the magnetic circuit. Because there is a magnetic material, there will be coils wound over it, and the coils are supposed to carry current. Therefore, they are going to produce flux in the core. And we know that if this is the direction of the current, suppose DC current first, then the direction of the current will be like this in the coil I. Suppose we have connected a DC source, this is the current. Then what happens? In the core, there will be a flux produced phi. Direction of the flux will be, as you know, you wrap your fingers around the coils and thumb will give you the direction of the flux produced. Of course, if it is a constant DC current, whatever flux will be produced inside the core, that too will have constant values. And how to estimate that flux? You know, we apply the Ampere circuital law to find out the flux produced in the core. For example, you see if I draw the sectional view of the core, like this, then if you draw the sectional view, the conductors can be shown to be like this. This is the coil sections. How many coil sections we will see? As is the number of turns of this one, and the direction of the current as shown can be shown by cross and dot like this. This will be cross current, cross, and this will be dot. Then the flux inside the core, what we do is we take a mean path of the flux, which I am showing by dotted lines. This is the flux and this red one is the length of the mean path, length of mean path of the flux. That length let me call L. If these are n, then Ampere's circuital law says that integral H dot d l over a closed path is equal to current enclosed. Is that? But in this case, the direction of H and L are same. Therefore, what will come out to be H into L, that dot product, because the direction of H and L as I move, they are same. Direction of H, direction of B, direction of phi, they are all same. And also length is like that. H dot d l means H into L should be equal to the current enclosed. How much current is enclosed by this path? N into I, N into I. We know this. So, I will not spend much of this time. So, this is N I by L. Its unit is ampere turns per meter. This will be the case. Once I know H, then I will calculate B. B will be equal to mu 0 mu r into H, where mu r is called the relative permeability of the core. And if the relationship between B and H is linear, then mu r is a constant value, and so this will be equal to mu 0 mu r, and for H I can write N I by L. Then then I go here, then the flux produced, which is in Weber, will be equal to B into the cross sectional area A. What is this A? A is this cross sectional area, that is this, through which flux will be flowing. So, this is A. Okay. So, this cross sectional area is perpendicular to the flux at any sections. Therefore, flux in Weber will be B into A, and B already I have calculated. So, I substitute that mu 0 mu r n I by L, this is H into area. Now, if you see this can be written as N I, I am sorry, if you see this, it will be N I and bring all the other things in the denominator, which will become 1 by mu 0 mu r L by A. Why I have written in this fashion is this, that this is the cause, I can identify this is the cause, and phi is the effect. Is not? I have supplied with MMF, and this magnetic circuit returns you a flux phi. And how to calculate that flux? MMF, this is called MMF, and this is called reluctance. And that is why the name magnetic circuit. In case of electrical circuit, I is equal to EMF by resistance. And if you recall, EMF is EMF, voltage, resistance is rho L by A. So, there is a striking similarity, and that is why it is called reluctance. Reluctance limits the value of the flux when you apply an MMF. Although the MMF and the flux in electrical circuit, as you know, the circuit is like this, resistance, and this is your EMF, say E by R, and this is the current. But in magnetic circuit, this MMF and this flux, wherever it is flowing, they are totally decoupled. I mean, it is not that flux is in the conductor. But nonetheless, this equation prompts us to simplify the matter and say that so far as calculation of MMF is concerned, you do it like this, Ni, and connect it by a reluctance, which is shown by a curly letter R, and here you show the flux. Although in this diagram I show there as if connected, but they are not in practice, but only prompted by this relationship corresponding in existing in the electrical circuit. It is better, that is why it is called magnetic circuit. So, if MMF is known, I will first calculate what is the reluctance. Reluctance of the magnetic circuit path depends upon its geometry, what is the length, what is the cross sectional area. Cross sectional area is this one of this is the cross sectional area. Then you calculate H Ni by L and then multiply it with mu 0 mu r to get B, then multiply with A and get that one. Therefore, in a simple excitation with DC current, this value of the flux whatever you will get, if you divide the MMF with reluctance, that too will be constant and its direction will be also fixed. In this case, it is clockwise. Okay. The reverse problem is also very simple. In that case, I will say that I want to create a certain amount of flux. What should be the current necessary? So, I will calculate reluctance. Reluctance into flux will give me N I, and if I know the number of turns, I will simply divide that N I with N to get the current necessary. Anyway, these are known stuff, and we have a magnetic circuit like this. Okay, and I will presume that you know about it. So, no question of further telling about it. Achha. Now, we will go to next page. Next page. Let us go to next page. Now, I will tell you that what happens if the same magnetic circuit, that is this one, this point you listen very carefully, and this is the most interesting thing. Sorry. I am sorry. Let me try to draw another thing here. That is the core I am drawing. You must understand. Why it is getting circled? Anyway, so suppose this is the core of the material. Let me draw slowly. Okay. And suppose you have let us consider a single coil, same magnetic circuit with n turns. But this time what I will do is this, I will connect it to an AC source. This is AC source of known voltage. For example, V 1 is equal to root 2, I am sorry, I will write it like this, V 1 t is equal to root 2 V 1, some say sin omega t or cos omega t, I will write it, applied voltage to this coil. Now, if you pass a sinusoidal voltage across the coil, in case of DC circuit, magnetic circuit, what I was telling, when the current is constant, then Ni you calculate MMF divided by reluctance, get the flux. But in AC circuit, AC magnetic circuit, the coil is connected across a AC supply voltage of known frequency, RMS value V 1 and supply frequency is F. Then what I am telling, first I will tell this statement, the flux in the core gets fixed. I mean, no question of once the supply voltage and RMS value is known, I mean we do not start telling that I will first calculate current, then calculate MMF, then divide that MMF with reluctance to get the flux, not like that. It will be the moment you apply a known RMS voltage at certain frequency f, where omega equal to 2 pi f and AC voltage across the coil, the level of flux which will be produced, which will be also time varying, it is expected, flux gets fixed. Now, what is the reason for that? Reason for that is, it is expected whatever current it draws, that will be also sinusoidally varying, because after all it is some sort of coil or inductance we have connected across an AC supply, some alternating current it will draw, and since current value and magnitude is changing with time, this phi too will be time dependent. Sometimes it will be flowing to clockwise, sometimes in the anticlockwise direction, sometimes it will be 0 when the instantaneous value of the current will be 0, and so on. But the moment an alternating flux is created inside the core of the coil, inside the core of this magnetic circuit, between these 2 points there appears an AC induced voltage. Suppose the number of turns of this coil is N, or say N 1, single coil N 1. Then according to Faraday, if there is a coil, if there is a time varying flux in the coil, then this coil itself become a seat of EMF, the value of instantaneous value of which is some minus n 1 d phi dt. About that sign it is not necessary so important, but what I am telling, this is the induced voltage, the flux linking the coil is changing with time, and therefore, there will be induced voltage across this coil. In this case, this flux is created by the current carried by the coil itself, but it does not matter. Faraday says, if there is a change of flux, rate of change of flux exists linking a coil, it is time varying, then between these 2 points it will become a seat of EMF. Negative sign is the Lenge's law. It tells that the polarity of this induced voltage will be such that it will try to oppose the very cause for which it is due. For example, this coil can be modeled as, here is your AC supply, V 1 t I have applied. Then what I am telling, across this coil, if I neglect the resistance of the coil, there appears another source here, and that induced voltage is E 1, and the polarity of this voltage will be such that if this side is d phi dt is positive, then it will try to oppose the cause. So, its polarity will be like this. Okay. Or in other words, what I am telling, so this thing can be now be modeled like this, applied voltage, and there is another induced EMF. In case of DC magnetic circuit, this E 1 will not be there. There is applied voltage which is constant. Of course, current will be limited by the resistance of the circuit, V by R. That is why current gets fixed I. But here what I am telling, the induced voltage in the coil will be same as the applied voltage. Only thing about the polarity, its polarity will be such that it will try to oppose the very cause, that is the flux, it will try to oppose it. What was the reason for flux existing and increasing? This current, it was increasing in the positive direction. So, it will try to reduce that value of the current. That was the reason. Anyway, after this I can say that in this loop KVL equation is to be satisfied. Therefore, applied RMS voltage must be equal to the RMS voltage of E 1. What else? Is not? Now, you see this flux will be some phi max, say let us forget about this cos omega t sin. Suppose I start with this one, phi max equal to sin omega t. Why I am assuming this? Because the circuit cannot but draw sinusoidally varying current. Let us call phi is equal to phi max sin omega t. If that be the case, then the RMS value of the induced voltage in the coil E 1 will be equal to N 1 d phi 1 dt. Okay. If you differentiate this, this will become equal to N 1 phi max omega some cos omega t. This will be the value of the induced voltage, is not? So, what will be the RMS value of that voltage? It will be the peak value of the voltage phi max omega by root 2. For omega, if you substitute 2 pi f, so it will become root 2 pi f phi max into N 1. See, I am not so much bothered about this minus 1, I should not struggle. My intention here is to calculate what is the RMS value of the induced voltage. Okay, differentiate it, peak value you get, divide by root 2 and that will give you RMS voltage. What I am telling is, in this circuit KVL equation must be satisfied. R is vanishingly small. So, applied RMS voltage must be equal to the induced RMS voltage. It cannot be other than that. Therefore, if the applied RMS voltage is V 1, it must be equal to root 2 pi f phi max into N 1, is not? It has to be, nothing other than that. So, what I have told you that in case of AC, it is the same magnetic circuit which I considered with DC excitation. If you connect it to an external voltage source which is alternating in nature sinusoidally and the RMS value of that applied voltage is known, current whatever flows has to be sinusoidal. Therefore, phi created inside the core of this magnetic material too will be time dependent and vary sinusoidally. And if this flux varies sinusoidally, then Faraday tells us that across these 2 points, there will be induced voltage. What is the magnitude of this induced voltage RMS value? That magnitude of this RMS voltage is root 2 pi f phi max into N 1. Applied RMS voltage is known V 1, induced RMS voltage is known capital E 1 and these two must be same because KVL is to be satisfied in the primary. If that be the case, In this equation, what are the things I know? V 1 is known, supply frequency is known, N 1 is known, number of turns, and your phi max is equal to V 1 by root 2 pi f into N 1. This is the crucial thing. As I told you, see, mind you, in case of alternating magnetic circuit, if you apply an AC voltage, the level of flux phi max is decided by whom? By the supply voltage RMS value, by the supply frequency and number of turns. So, is it not something different from DC circuit? DC circuit, you apply some known current, DC current in the circuit, calculate MMF, divide by reluctance, get the flux. But here, it is somewhat interesting. The moment you connect an AC voltage V 1 and F, I can tell you the flux is sinusoidally varying. What is the maximum value of that flux? Is fixed, it is this one. Therefore, this phi max, how much will be produced inside the core, is decided. I do not have any control over it. In fact, I will go a step ahead. I will tell you, if this core material, it has got a permeability of mu r 1, you replace this core material with another magnetic material having relative permeability mu r 2, then also phi max is V 1 by this one. So, no matter what is the kind of magnetic material it is, good magnetic material, bad magnetic material, the moment supply RMS voltage and supply frequency are known, phi max in the core is decided, a very crucial point to go ahead with the concept of transformer. We will continue with that. Thank you.